Hello everyone. Today I'll be discussing the concept of code smell. Last December, I had the opportunity to give a tech session at GDG Dhaka. It was an interesting time as the World Cup football matches were taking place. Right after the semi-final match, I immediately began preparing my presentation. I quickly gathered some examples from the internet and completed my slides. While all the content is available online, some of you requested a video recording of the session. Unfortunately, the session was not recorded, so I'll be presenting the same slides with the same content today. In this slide, I have included a picture of Lionel Messi, the legendary Argentine player. Being a die-hard fan of Argentina and Messi, I wanted to showcase him wearing a jersey with two stars. At that particular time, Argentina hadn't played the final match yet, but I imagined a scenario where they would win for the third time. The example helped us to understand the concept of duplicate code in the context of game programming. Imagine if the World Cup jersey represented our game programming code and Argentina winning the third time required adding an extra star to the jersey. Now, if we had coded the jersey in multiple places instead of just one, we would face a problem. Any change made in one instance of the code would need to be replicated in all the other instances. This highlights the issue of duplicate coding. Duplicate code is risky because it significantly increases the chance of introducing bugs. If you modify one instance of the code but neglect to update the others, inconsistencies arise, leading to potential errors and system malfunctions. But don't worry, in the later part of the presentation, I will provide you with example to illustrate the consequence of duplicate code and demonstrate how we can mitigate this problem. Let's move on to the next slide to delve deeper into the topic. I'm sure you are familiar with the Bangla proverb Morsha Marte Kamandaga. Here we have humorous picture that perfectly captures a Bangla proverb Morsha Marte Kamandaga, which translates to using a cannon to kill a mosquito. It's a light-hearted way to introduce the concept we're about to discuss. Let's talk about the pros of the long methods and large classes in programming. Long method can be quite a challenge to understand. Just like using a cannon to swat a tiny mosquito, having lengthy and convoluted methods in your code can make it harder for others, including yourself, to grasp their purpose and functionality. It's like trying to decipher a complex puzzle without any clear hints. So it's generally advisable to keep your method concise and focused, making them easier to comprehend and maintain. As for large classes, they suffer from a similar problem. They attempt to do too much, resembling our soldier who is holding a cannon to deal with a tiny insect. When a class takes on excessive responsibility, it's become difficult to maintain cohesion within the code. In other words, the class loses its clear and defined purpose, making it harder to manage and modify. It's like trying to juggle multiple tasks at once and struggling to give each one the attention it deserves. However, it's worth noting that the traditional performance concerns associated with having numerous small methods are largely obsolete in modern programming languages and environments. So the argument against long method isn't solely based on the performance issues, but rather on the importance of code readability and maintainability. Let's move on to the next slide, but don't worry, we'll show some concrete example that will help solidify this concept. Imagine you are in a relationship, and I'm sure many of you can relate to this scenario. You have probably encountered those amusing situations when your partner, whether it's your boyfriend or girlfriend, come up with a massive list of demands. It can be quite overwhelming, but deep down you're willing to entertain them if they're requested just one or two things. Now, let's draw a parallel between this relatable situation and a common issue in programming, the long parameter list. Similar to the never-ending list of demands, having a long parameter list in your code can be challenging to understand and manage. It can quickly become inconsistent, just like trying to keep track of all the different items your partner wants. To combat this issue, renowned software engineer Robert C. Martin in his book Clean Code suggests refactoring methods with more than 3 parameters. And if a method contains more than 4 parameters, it's time to start questioning its design and potential for improvement. Another issue we encounter is divergent change. Have you ever realized that when you make a modification to a particular class, you end up having to alter numerous unrelated methods? It's like when you add a new product type, you have to change the method for finding, displaying, and ordering products. It can be quite frustrating. Let's delve into the intriguing concept of lazy classes and speculative generality. In the world of programming, we often come across classes that don't quite capture the coder interest or serve a meaningful purpose. It's like having something in a relationship that doesn't quite add value and might even become a burden. In such cases, it's important to assess whether these classes should be dropped. Lazy class, as the name suggests, refer to a class that doesn't do enough to catch coder interest. It's like having a character in a story who doesn't contribute much to the plot. In programming, a lazy class can be challenging to understand and maintain. It takes time and resources to work with and can hinder the overall progress of the code base. Therefore, it's often recommended to evaluate whether a class that doesn't bring sufficient value should be dropped. This could be a class that was downsized during a previous refactoring or represented a planned functionality that didn't pan out. By removing such classes, we can simplify the code base and make it more maintainable. Now let's shift our attention to the speculative generality. It's like saying, ah, I think we might need the ability to do this kind of thing someday. Speculative generality smells are interesting because they are usually created by experienced programmers. These programmers, with their vast knowledge and foresight, often try to anticipate every possible future scenario in their code. However, this can lead to over-engineering and adding unnecessary complexity to the system. It's important to strike a balance between accommodating future needs and focusing on the current requirements. By avoiding speculative generality, we can keep our code base lean and avoid the pitfalls of unnecessary complexity. Let's now shift our focus to another code smell called temporary field. Temporary field refer to attributes on an object that are only set under specific conditions. However, the object itself should ideally have all its attributes intact. Imagine a scenario where a variable is defined in the scope of a class instead of being confined to the scope of a method where it truly belongs. This violates the principle of information hiding and can lead to confusion and inefficiency in our code. Temporary fields and the code that operates on them can be extracted and put into a separate class using the extract class technique. This way, we create a method object achieving the same result as if we were to perform replace method with method object. By organizing the code in this manner, we can effectively address the issue caused by the temporary fields. Another approach to handling temporary field is to introduce a null object and integrate it in the place of the conditional code used to check the existence of the temporary field values. This helps simplify the code and avoid unnecessary conditional statements. By addressing temporary fields, we adhere to good programming practice and maintain the integrity of our objects. We ensure that each object has all the necessary attributes and that they are appropriately encapsulated within the scope they belong to. Now, let's delve into the concept of refused bequest. which can be illustrated by this amusing picture of a dog and a chair. Both the dog and the chair have legs, but it's clear that they shouldn't have the same common parent. Just like in programming, when a subclass ignores most of the functionality provided by its superclass, it raises concern. Refuse because occurs when a subclass fails to fully utilize or incorporate the functionality inherited from its superclass. It's like having a child who doesn't quite fit the mold of their parent. In object-oriented programming, subclassing should adhere to the is-a relationship, where the child class is a specialized version of the parent class. However, if the subclass ends up ignoring or overriding most of the inherited functionality, it is clear sign that it shouldn't be a subclass of the parent class in the first place. The purpose of creating subclass is to introduce or modify functionality while maintaining the core characteristics inherited from the superclass. By refusing the bequest, we violate the principle of inheritance and risk creating an inconsistent and confusing code base. To address the issue of refused bequest, it is essential to revalidate the class hierarchy and ensure that subclasses truly inherit and extend the inherited functionality. If a subclass doesn't fit the mold of the superclass or requires significant modification, it may be more appropriate to restructure the inheritance relationship or consider other design patterns that better align with the specific requirements. Now let's talk about the familiar aspect of code comments. We often encounter comments in code, and while they can serve as a helpful explanation or clarifications, they can also be used to hide bad codes. It's like using deodorant to mask an unpleasant smell. Comment, when misused or overused, can become a code smell themselves. Instead of addressing the underlying issues and improving the code clarity, comments may serve as a band-aid solution to cover up poorly written or confusing code. Relying heavily on comments to explain code can indicate a lack of readability and maintainability in the code base. Ideally, code should be self-explanatory and easy to understand without excessive reliance on comments. Well-written code should communicate its purpose and functionality effectively, reducing the need for extensive comments. While comments can be useful in certain situations, such as documenting complex algorithms or providing legal disclaimers, they should not be relied upon as a crutch for poorly written code. To address the issue of excessive or misleading comments, it's crucial to focus on writing clean and self-explanatory code. By following coding best practices, using meaningful variable and function names, and applying proper code structure techniques, we can reduce the need for excessive comments and improve the overall readability of our code. Alright, let's take a moment to discuss the classifications of code smells. We have already covered a few of them, but there are many more to explore. These code smells can be grouped into different categories based on their characteristics and impact on the code base. The first category is bloaters, which include code smells such as long method, large class, primitive obsession, long parameter list, and data cramps. These smells often result in bloated, hard to maintain code that lacks clarity and consistency. Next, we have object-oriented abusers, which compromise code smells like alternative classes, refuse bequest, switch statements, temporary failed, and others. These smells indicate a violation of object-oriented principles and can lead to a code that is inflexible and difficult to extend or modify. Change preventers are another category of code smell that includes divergent change, parallel inheritance hierarchy, shotgun surgery, and others. These smells make it challenging to introduce changes or modifications in the code base, increasing the risk of introducing bugs or causing unintended consequences. Dispensables, as the name suggests, encompasses code smells that are unnecessary or redundant, such as comments, duplicate code, data class, dead code, lazy class, speculative generality, and more. These smells clutter the code base and can be removed to improve code readability and maintainability. Lastly, we have couplers, which include code smells like feature envy, inappropriate intimacy, incomplete library class, message chain, and middleman. These smells indicate tight coupling between classes or excessive dependencies, making the code base more difficult to understand and modify. While we have covered a few code smells today, there are numerous resources available online that provide comprehensive lists and explanations of these code smells. You can explore further by doing a simple Google search to gain a deeper understanding of each code smell and its implications. In the later part of this presentation, I will share some examples of these code smells that I have collected from various sources. Remember, these examples are readily available online, so you can also find them through a quick Google search. By examining these examples, we can better comprehend the practical manifestation of this charisma and learn effective strategies to address them. Have you ever wondered why even good developers sometimes end up writing bad software? Well, there are few reasons that contribute to this phenomenon. Firstly, over time, requirements change. Software projects are dynamic, and as the needs and expectations evolve, it becomes challenging to modify existing code and maintain optimal design. What once seems like a good solution may no longer be suitable for current requirements. This can lead to code that is difficult to understand, modify, and maintain, resulting in suboptimal designs. Secondly, developers often face time and budget constraints, which can tempt them to take shortcuts. In an effort to save time and money, they may opt for quick fixes or temporary solutions that may not adhere to best practices or result in optimal code quality. These shortcuts can accumulate over time, leading to a code base filled with technical debt and potential issues down the line. Lastly, learning is an ongoing process, and developers often discover better ways to doing things as they gain experience. Just like painting a room, the second time is often better than the first time because lessons are learned along the way. Similarly, developers may realize that there are more efficient or elegant approaches to solve problems after they have already written the initial version of the software. This continuous learning process contributes to the evolution of coding practices and can result in earlier code being preserved as a less optimal. Hindsight. It's important to remember that writing good software is a continuous journey, and even experienced developers face challenges and make mistakes along the way. The key to recognize and address these challenges by adopting practice such as refactoring, continuous learning, and code reviews, which can help improve the overall quality of the software being developed. Refactoring is crucial practice in software development that allows us to improve the quality of the code without altering its external behavior. It involves making changes to the internal structure of the codebase to enhance its readability, maintainability, and extensibility. When we refactor code, we aim to make it easier to understand, modify, and add new features to without changing its observable behavior from the perspective of users or other parts of the system. In other words, the external behavior of the software remains the same after refactoring. By focusing on the internal structure, we can address code smells, eliminate redundancies, simplify complex logic, and create a more robust foundation for the future development. Refactoring helps us reduce technical depth, improve code maintainability, and enhance the overall quality of the software. It is important to note that refactoring is not about adding new features or fixing bugs directly. Instead, it is deliberate process of restructuring the code base to make it more efficient, readable, and adaptable. Through refactoring, we can eliminate code smells, improve the organizational and clarity of the code, and optimize its performance. Refactoring is an iterative process that can be applied to small selection of code or larger components. It is typically done incrementally, ensuring that each step of the refactoring process is tested and validated to ensure the code remains functional. By regularly practicing refactoring, developers can maintain a healthy code base, improving their own code skill and create software that easier to maintain and evolve over time. It is an essential tool in the pursuit of writing clean, efficient, and high quality code. We have already discussed that it is important to understand that the goal of refactoring is not to add new functionality. Instead, the main objective of refactoring is to make the code easier to maintain and work with in the future. The image on the slide is an illustration of symbolize the potential risk associated with refactoring. We will now discuss these dangers in detail on the next slide. Refactoring, just like any other software modification, can introduce problems or bugs. Whenever we make changes to the code base, there is a possibility of unintended consequences. However, it is important to note that the risk associated with the refactoring can be mitigated through proper planning, testing, and following best practices. Management of risk concern about perceived risk and costs associated with refactoring. They may question why we are investing time and resources in refactoring if it doesn't result in immediate visible changes to the software. Here are some common concerns raised by the management. Refactoring adds risk. Management may argue that by modifying the code, we are potentially introduce new bugs or breaking existing functionality. While this is a valid concern, it's crucial to emphasize that refactoring, when done correctly and accompanied by thorough testing, reduces the overall risk in the long run. It improves code quality, making it easier to maintain and less prone to the future issues. It's expensive. From a management perspective, refactoring may seem costly as it requires development time and resources without immediately visible external changes. However, it's important to convey the long-term benefits of refactoring, such as improved maintainability, reduced technical debt, and increased productivity. By investing refactoring, we create a solid foundation for future development, enabling faster future implementation and easier bug fixes. Why we are doing this? Management might question the need for refactoring if the software is currently functioning. Refactoring is a valuable practice because we recognize that achieving the perfect design right from the start is challenging. By embracing refactoring, we can unlock numerous benefits that significantly enhance the quality and maintainability of our code base. Here are some advantages of refactoring. Code size reduction. Refactoring allows us to eliminate unnecessary code and optimize the structure. By removing redundant or obsolete code, we can streamline the code base, making it more concise and easier to comprehend. This reduction in code size is not improves readability but also enhances performances and reduces the chances of introducing bugs. Restructuring confusing code. During the refactoring process, we restructure complex and convoluted code into simpler, more understandable constructs. By breaking down large method or classes into smaller, well-defined components, we enhance the code clarity and make it easier for developer to navigate and maintain. The restructuring contributes to improve readability and facilitates better collaboration among team members. Improve maintainability. The primary goal of refactoring is to enhance the maintainability of the code base. By refactoring, we proactively address code smells and design flaws, making the code easier to understand, modify, and extend. As requirements evolve over time, having a maintainable code base becomes crucial. Refactoring enables us to adapt the changing requirements more efficiently, reducing the time and effort required to future enhancement or bug fix. In the world of software development, there exists a wide range of well-known refactoring techniques that have been proven effective over time. It is highly recommended that you become familiar with these techniques before attempting to invent your own. By leveraging the knowledge and experience from the software development community, you can benefit from established practices and avoid reinventing the wheel. There is a valuable resource known as the Refactoring Catalog that provides an extensive collection of these techniques. I encourage you to explore this catalog and delve into the various refactoring techniques it offers. Knowing when to refactor is a key aspect of maintaining a healthy and robust code base. Here are a couple of scenarios where refactoring is beneficial. Firstly, you should consider refactoring whenever you come across a better way to accomplish a task or improve the code overall quality. When we say better, we mean making the code easier to understand and modify in the future. Refactoring allows us to enhance the design, eliminate code smells, and improve the overall maintainability of the software. Secondly, it is important to ensure that you can refactor without breaking the existing code. This is where unit tests play a crucial role. By having comprehensive unit tests in place, you can refactor with confidence, knowing that any unintended side effects or regressions will be captured by the tests. The tests act as a safety net, allowing you to make changes to the code while maintaining its correctness and functionality. So, if you spot an opportunity to improve the code base and make it more maintainable, go ahead and refactor. Just remember to do so within the safety net of unit tests. Refactoring should be an ongoing practice throughout the development process, helping you continuously enhance the code's quality and adapt to the changing requirements. Ah, this one is a classic. Brace yourself, flocks, because I'm about to take you back to one of my all-time favorite memes. I still remember the uproarious laughter and electrifying atmosphere in the room during my live presentation of this slide. It was absolutely hilarious. So, there is a mighty lion peacefully dozing off, and along comes a mischievous monkey armed with a stick. The audience burst into laughter as they anticipate some wild and unpredictable shenanigans about to unfold. This meme perfectly captures a scenario where we may choose not to refactor our code. Now let's dive into the humorously logical side of things. Imagine that the lion represents a smoothly running rock-solid code base. It's like a Turing machine, flawlessly executing tasks without a hiccup. And here's our cheeky monkey, holding the stick, all eager to stir up trouble by making unnecessary changes to the code. But hold on a second. Why would we want to disturb the peace if everything is working like a charm? There are times when we need to pause and consider whether it's worth waking the lion from its peaceful slumber. One such instance is when we have stable code that doesn't require any further modifications. If the system is humming along without any issues and there are no new requirements in the site, why risk disrupting its harmony? Another scenario is when we find ourselves dealing with someone else's codes. Unless we have their explicit agreement or ownership over the code, it's best not to go swelling the refactoring stick around. We wouldn't want the lion's roar of disapproval, would we? However, in agile programming, where collaboration is shared ownership are valued, this becomes less of a concern. Now, let's get down to business. Refactoring is like trading on a delicate path, and we want to ensure a smooth journey, so here's how it goes. Step 1, make a small change. And I mean tiny, my friend. We're talking about a single refactoring at a time. We don't want to stir up a coding storm, do we? So let's focus on one improvement, whether it's simplifying a method, untangling a mess of code, or giving it a fancy makeover. Thinking of it as carefully rearranging the furniture in your coding mention. Step 2. After making that small change, it's time to put our code through its paces. Run all the tests and see if everything still works like a charm. It's like giving our code a thorough checkup, making sure it's healthy and ready to take on the world. We don't want any surprise popping up, right? Now, here where things can go two ways. Scenario 1, hooray! Everything passes with flying colors, no bugs, no glitches, just smooth sailing. In that case, my friend, we can confidently move on to the next refactoring adventure. It's like adding another layer of brilliance to our masterpiece, steadily transforming it into a work of art. Scenario 2. Oh, the tests reveal a little hiccup, a bug lurking in the shadows. But fret not, we're here to save the day. We'll roll up our sleeves, put on our debugging hats, and fix that problem. We want to keep our system sailing smoothly after all. And if by any chance we realize that our change wasn't the best move, we can always hit the magical undo button and bring back the working version of our code. Safety first. Switch statements are a rare sight in properly designed object-oriented code. When we encounter a switch statement, it often raises a red flag as bad smell in our code. However, it is important to note that not all uses of switch statements are inherently bad, but there is a specific scenario where they should be avoided, distinguishing between various kinds of objects. In the given example, we have a class called animal. With a switch statement inside the getSkin method, the switch statement checks the value of the myKind variable to determine the type of skin and returns the corresponding string. While this implementation may seem fine initially, it violates the principle of object-oriented design. Now we can see the complete refactored code. Each subclass, mammal, bird, and reptile, has its own implementation of the getSkin method, returning the appropriate skin type. By utilizing subclasses, we eliminate the need for the switch statement. We now have a more extensible and maintainable code base. So, how does this refactoring improve our code? Well, here are a few key points. Adding a new animal type such as amphibian becomes easier. We don't need to revise and recompile the existing code. We can simply create a new subclass for the new animal type, implement the getSkin method accordingly, and our code remains intact. Mammals, birds, and reptiles are likely to differ in other way as well. With the separate subclasses, we have already separated their specific behaviors and attributes. This means we won't need additional switch assessment or flags to differentiate between animal types. We have embraced the essence of object-oriented programming by utilizing objects as they were intended. By employing subclasses, we are leveraging the power of inheritance and polymorphism. Our code becomes more organized, easier to understand, and aligned with the principle of object-oriented design. In summary, throughout this refactoring, we have eliminated the switch statement, introduced subclasses for different animal types, and improved the extensibility and maintainability of our code base. It's a win-win situation. All right, folks, let's talk about the importance of encapsulating fields in our object-oriented applications. It's time to bid farewell to uncapsulated data and embrace the power of proper encapsulation. In the given example, we have a class called course, which initially exposed a public list called students. Now, this might not seem like a big deal at first, but unencapsulated data can lead to various issues down the line. Here, anyone can access and modify the student list directly without any checks or control. But fear not, we have a solution that will not only enhance the design but also promote better code organization and maintainability. In the improved code, we have encapsulated the list of students by making it private. We have also introduced getter and setter method to provide control access to this encapsulated data. The getStudents method allows us to retrieve the list while the setStudents method enables us to modify it. By encapsulating the field and using getter and setter method, we ensure that any access or modification to the student list goes through proper check and controls. It gives us the flexibility to add validation or perform additional operation in the future without affecting the external code that interacts with the class. For example, previously someone could directly access course.student.size to get the class size, but with encapsulation, we now use course.getStudents.size to retrieve the size, which provides an extra layer of abstraction and encapsulation. So, why is encapsulation so important? It promotes data hiding, prevents unauthorized access, and allows us to maintain control over our class internal state. It's also ensure that we have a clear and consistent way to interact with the data, making our code more reliable, maintainable, and adaptable. All right, let's tackle the challenge of encapsulating fields, especially when dealing with classes that have multiple fields. It can be quite a pain to set up encapsulation for each individual field, but fear not, my friends, we have some handy tools and techniques at our disposal to make this process a breeze. One of the key tools we have leveraged is the use of refactoring tools provided by a popular IDE like IntelliJ IDEA. These tools offer automated refactoring capabilities that can greatly simplify the task of encapsulating fields. So if you're using IntelliJ IDEA or a similar IDE, I highly recommend it exploring the refactoring example specific to the encapsulating fields. In addition to refactoring tools, we have a couple of other techniques like rename method. This technique allows us to rename methods without breaking the code that calls them. It's particularly useful when we want to align the method name with the encapsulated field's purpose or when we want to enhance the code readability. Change method parameters. Sometimes we might need to modify the parameters of the method associated with an encapsulated field. This technique allows us to make those changes while ensuring the code calling the method remains intact. Now, let's explore the concept of extracting a class, which involves breaking one class into two or more separate classes. This technique is particularly useful when we encounter a scenario where certain responsibilities within a class can be better managed by individual classes. Let's dive into an example to understand this better. In the given example, we have a class called customer that contains fields for customer's name, work phone area code, and work phone number. However, having the phone detail as a part of customer class is not an ideal object-oriented model, and it's also violate the single responsibility principle. To improve the design, we can extract the phone details into separate class called phone. This allows us to adhere the single responsibility principle and create more focused classes. In the refactored code, we have created new class phone which is encapsulated the area code and the phone number fields. The customer class no longer directly holds the work phone details. Instead, it references an instance of a phone class. The refactoring improves the overall design by dividing responsibilities more effectively. The customer class now focuses solely on the customer related information, while the phone class is responsible for handling phone details. Each class has a clear and distinct purpose, making our code more maintainable, extensible, and aligned with the principle of object oriented design. By extracting the phone details into a separate class, we have achieved better code organization and ensured that each class has a single responsibility. This makes our code more modular, easier to understand, and paves the way for future enhancements or modification to specific aspects of our application. Now, let's explore the concept of extracting an interface from a class. The technique allows us to define a separate interface that represents a subset of behaviors or responsibility of a class. By doing so, we adhere to the interface segregation design principle, which emphasizes having a specialized interface rather than one multi-purpose interface. In the given example, we have a class called customer that has a method toXML for generating an XML representation of customer data. However, having the toXML method as a part of customer interface violates the interface segregation principle. To improve this design, we can extract an interface from the customer class. In this case, we'll call it the serXML to represent the serialization to XML behavior. In the refactor code, we have extracted an interface called serXML that declared the toXML method. The customer class now implements this interface, indicating that it provides the serialization to XML behavior. Similarly, we might do it for JSON. By separating this behavior into an interface, we adhere to the interface segregation principle, allowing clients to depend on specific interfaces tailored to their needs. Okay. This technique comes into play when methods become overloaded with functionality, making them hard to understand, error-prone, and difficult to reuse. By breaking down complex methods into smaller, well-named ones and enhance code readability and maintainability, enabling us to reduce duplication and promote reusability. Consider the original method in the customer class. Here, the foo method is doing multiple things, including computing a score. To improve this, we can extract this score calculation logic into its own method. In the refactored version, the complex scoring logic has been extracted into the compute score method, which actually takes parameters and return the computed score. The foo method now calls this extracted method, making the code more concise and understandable. This refactoring not only enhances the readability of the foo method but also allows us the compute score logic to be reused elsewhere in the codebase if needed. It's a win-win situation, reducing complexity and enabling better code reuse. By adopting the extract method technique, we break down intricate algorithms or processes into smaller, manageable pieces, making our code base more modular, understandable, and maintainable. It's a fundamental step towards writing clean, efficient, and reusable code. Let's explore the extract slab class refactoring technique, a strategy employed when a class accumulates features that are only relevant in specialized instances. By creating specialized subclasses and assigning these features to the appropriate subclass, we make the original class more abstract, adhering to the principle of designing to abstractions. Consider the original person class. In the scenario, job title is a feature specific to employees. To enhance the design, we can create a more abstract person class. Then we can derive a specialized employee subclass that includes the job title attribute. In the refactoring, the common attributes and behaviors are kept in the more abstract person class, making it a generalized representation of a person. The specific feature related to employees, such as job title, are encapsulated within the employee subclass. By employing extract subclass, we ensure that our classes are more focused and follow the single responsibility principle. Person deals with properties shared by all the individuals, while employee handles properties unique to employees. The separation not only enhances clarity but also allows for easier extension in the future. New specialized subclasses can be introduced without modifying the general person class, promoting a flexible and adaptable code base. Remember, good design revolves around abstracting commonalities and encapsulating variabilities. Extracting subclass is a powerful way to achieve this goal, leading to a more modular and maintainable code base. Let's explore extract superclass refactoring technique, a valuable approach when you identify common features shared by multiple classes. By abstracting these shared features into a superclass, you promote a more cohesive and organized design, reducing code duplication and allowing client to interact with a unified abstraction. Consider the original employee and student class. Both classes have a shared attribute name. To enhance the design, we can create an abstract person class containing the common properties. Now, the employee and the student class extends the person class, inheriting the shared name attribute while retaining their specific attributes. With this refactoring, we have eliminated duplicate code related to the name attribute and created clear inheritance hierarchy. The person class acts as a superclass encapsulating shared properties, and both employee and students are specialized subclass representing specific roles. By embracing extract superclass, we ensure that our code is more maintainable as changes to the shared attributes or behaviors can be made in one central location. This technique enhances code consistency and readability while enabling a more intuitive understanding of the relationship between classes. Let's explore the form template method refactoring technique, a powerful approach to eliminate duplicate code in the method across subclasses. When you notice methods in subclasses that follow the same steps but do different things in each step, you can create template method for those steps in the base class, promoting code reusability and ensuring a consistent workflow. Consider the initial person and company classes. To eliminate the duplicate code, we create a template method print name and details in the party class. In this refactoring, the common print name and details method is moved to the party class as a template method. The abstract methods print name and print details in the party class are implemented differently in each subclass. Now, the subclass don't need to duplicate the common printing logic, promoting a clear and more maintainable design. By employing form template method refactoring, you enhance the code consistency, simplify maintenance, and ensure a unified behavior across subclasses. It's a fundamental technique for creating a structured and cohesive class hierarchy. Let's dive into the move method refactoring technique. A strategy employed when a method is one class relies more on another class than the class it's defined in. By moving the method to the class it interacts with most, you enhance cohesion and minimize dependencies, leading to a more modular and loosely coupled design. Consider the original student and course classes. In this scenario, the is taking method in the student classes relies heavily on the course classes. To enhance cohesion and reduce dependencies, we move the method to the course class. Now the is taking method resides in the course class where it directly interacts with the student's leads. The student class no longer need to know about the internal structure of the course class, promoting a more cohesive design and reducing the coupling between the two classes. Let's explore the introduce null object refactoring technique, a valuable strategy for handling default behavior without relying on null references. By using inheritance to create a specialized null object class, you can simplify your code and improve its readability and maintainability. Consider the original user class where null is used for default behavior. To avoid using null for default behavior, we create a null user class that inherits from the user. In this refactoring, the null user class is introduced. When a null check is required, an instance of null user can be used instead of a null reference. By utilizing inheritance, you ensure that the default behavior, which means plan.basic, is encapsulated within the null user class, eliminating the need for explicit null checks. Let's delve into the replace error code with exception refactoring technique, a powerful way to handle exception case in your methods. Instead of returning a special error code which can lead to an unclear and error-prone code, exceptions provide a more structured and expressive approach to dealing with errors. Consider the original method that returns an error code. To enhance clarity and make error handling more robust, we use exceptions. In the refactoring, the method now throws a balance exception if the withdrawal amount exceeds the balance. If using exceptions, you clearly communicate exceptional condition, making it easier for the caller of the method to handle errors effectively. This approach is also encourage a more structured error handling mechanism, promoting clear and more maintainable code. In some scenario, catching exceptions can be less efficient than using conditional statement, especially when dealing with predictable exceptional cases. Let's explore the replace exception with test refactoring technique, which involves replacing caught exception with explicit checks for better performance and code clarity. Consider the original method that catches an array index out of bound exception. Instead of catching the exception, we can use a straightforward if statement to handle the boundary condition. By employing this refactoring, you improve the performance of your code and make the logic more explicit. Conditional checks are typically faster and convey the intent clearly without the overhead of exception handling. This approach enhances both the speed and readability of your code, leading to a more efficient and maintainable software system. In the realm of code clarity and simplicity, the nested conditional with guard refactoring shines. When a method's conditional behavior obscures the normal path of execution, utilizing guard clauses can enhance readability significantly. Look at the original method with nested conditionals. With the guard clauses, the method becomes streamlined and more expressive. By employing guard clauses, you enhance the readability of your code by eliminating nested conditionals. Each special case is handled independently, making the normal flow of the code explicit and reducing the cognitive load for anyone reading the code. This approach simplifies the logic and clarifies the intent, leading to more maintainable and understandable code. In the pursuit of code clarity and maintainability, the replace parameter with explicit method refactoring technique plays a pivotal role. When a method exhibits different behavior based on an enumerated parameter, creating distinct method for each parameter value simplifies the code and enhances readability. Consider the original method with the parameter-based branching. By employing the replace parameter with explicit method refactoring, the code transforms into clear explicit methods. Each distinct behavior previously dependent on the parameter now resides within its own method. This approach enhances code readability, simplifies maintenance, and ensures that each method has a single well-defined purpose. By replacing parameters with explicit methods, you create a more intuitive and self-explanatory API, forecasting a robust and understandable code base. In the pursuit of code clarity and flexibility, the replace temp with query refactoring technique proves invaluable. When you find yourself employing temporary variable to store results of expressions, extracting this expression into methods can enhance code readability and maintainability. Consider the original code utilizing a temporary variable. By applying replace temp with query, the code transformed by replacing the temporary variable with a method call. With this transformation, the temporary variable base price is replaced by the method called base price, making the code more expressive and self-explanatory. Additionally, the extracted method can now be utilized in various contexts, promoting code reuse and allowing for future refactorings. In the realm of code clarity and self-documenting code, the rename variable or method refactoring stands as a fundamental yet powerful technique. A well-chosen name for variables and methods significantly enhance the readability and understanding of your code base. Consider the original code with a cryptic method name. By embracing the rename variable or method refactoring, the method is given a clear descriptive name. Ladies and gentlemen, thank you for joining me on this exploration of essential code refactoring techniques. Your journey towards writing clean, maintainable, and efficient code has just begun. Feel free to reach out, share your thoughts, and engage in discussions. I value your feedback and insight. Let's continue these conversations. I particularly encourage you to connect with me on LinkedIn as it's my preferred platform for professional networking. Your questions, suggestions, and comments are not just welcome but highly appreciated. Let's continue to learn and grow together in the vast world of software development. Thank you once again and happy coding.